Okay, Assalamu alaikum, student. Today we will start Turing machine. That's most powerful machine in the theoretical computer science. And we have learned about the concept of NFA DFA, which is the machine without memory, and then PDA, push down automata, the machine which is having stack as a storage uh, with the limited capability of storage where we can store the data in the one direction. We can push the data and we can pop the data. But the third one is a Turing machine, which is most powerful machine. The current computer is a real implementation of Turing machine. So Turing machine will use random memory, and we can insert the data on any point we can fetch the data from any point, and this will also provide a very flexibility to compute complex problem which is not computable by NFA or DFA or any PDA machine. So with respect to the language hierarchy, so far we have covered about the regular language, where the regular A star, B star, this type of language where we don't need to require storage. We don't need to measure the thing in this way that we need storage. Then we covered about the context-free language, where A and B and where we need a storage so that we can compare how many A's are there so that we can have as many B's as were there A's. So we can compare the A and B are equal, and we can compare the WW reverse. We can compare what we have pushed. We have to pop the same type of symbol. So WW reverse are computable, A and B and are computable with the help of PDA machine, push down automata. But when we move onwards, there are some complex problems. Similar classes are complex problem which can be resolved with the high power machine. Relatively constrained problems so far, analyzing protocol. Let's suppose we want to analyze which type of protocol is being used. If we are searching the text, we want to tokenize the text. We have to break up the string into tokens, and then we need to compare the tokens, and then we come up with the result if the string is matched or not. We need to design some parsing program, like we are using the C++, Java, etc. We know that we have parser backend of the programming language which match the token word, which match the syntax, and then execute the syntax according to the instruction provided from the developer. And the instruction are matched, yeah, either are a keyword or we can say literal, or the variable is stored, a equal sign is correct or not, if condition is correct or not, semicolon is missing. These things are checked using the parser. We can design compiler after learning the Turing machine, and we can define such type of language which can be acceptable by the any type of compiler such as Java compiler, C++ compiler, etc. What are the languages defined by the complex computation devices such as a computer? We have defined the hierarchy of languages which are regular, context-free, non-context-free, context-sensitive. We will continue towards the outer bound of the context-free language, where we have to measure the A and B and Cn. How we can compute the language which have the strings of type A and B and Cn. Number of A's are equal to number of B, and number of B is equal to number of C, and A comes first, B comes second, and C comes third, in such pattern. We don't have computation. We learn about the PDA, and we come up with the result when we applying the pumping lemma that push-down automata cannot compute this type of language. A and B and C is not computable by the pumping lemma, push-down automata. So continuing to do with respect to that point, what is the machine for that type of language? What is the machine for WW? What are other computational problem are solved by? So for that we learn about we will learn today the Turing machine. The solution is Turing machine. The answer of that question, that which machine will compute that type of problem, is Turing machine. What is Turing machine? How it works? What type of Turing machine we will learn in the coming lectures. Is a basic model of Turing machine shown in the slide. Here you can say a Turing machine is a simple machine which consists of simple automaton, which is control unit, as shown in the figure, which is similar to the NFA or DFA. But it also contains a tape where the symbols are stored. We can store the symbol, we can read the symbol, we can write the symbol. It's a tape and it is infinite tape of both sides. Here you can see dot 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 dot. It means the tape has infinite length on both sides. Here you can see a head. This pointer is called head. And what you can do with the help of head, you can read and write. It's a read head and also a write head. So you can read and write using this head on the Turing machine. And who will control when to read, when to write, how to read, how to write? It's a control structure. This automaton will provide you how you will control the instructions. So here you can see that tape have no boundaries. It's infinite length tape. It contains any type, any number of symbols, infinite symbols, and not on one side, both sides. It has infinite symbols on both sides. You can move on the right side up to infinity. You can move left side up to infinity. Head movement are there two head movement. You can move left, you can move right. So there are two movement. You can move right, then you can move left, then you can move left, then you can move left, then you can move right. You can have any dependence. You don't have any dependency, but dependency on that when you will move left or right dependent on the controller structure. So when we are writing this transition on the controller structure or control unit, the head at each transition timestamp will do three tasks. One, it will read a symbol. Second, write a symbol. Where it will read symbol from the input tape. And where it will write the symbol, it will write symbol on the tape. And then move left or right. At one time, it will move at left or right. It cannot move both sides. On one transition, you can show that either it will move left or it will move to right. Here are some examples. On the time 0, on the tape, there is an input A, B, A, C. So A, B, A, C is the input on the tape. There are some other input, but we are not reading that. Let's suppose we have only A, B, A, C. Our head is on A. Depending on the transition, we will read A and then we write K and then move left. So there will be three tasks. Read A, write K and move left. This is the left side. We will move from A to B. After writing or converting A into K, we will convert A into K. How we will convert? We will read A, there's a A. It means we are identifying where we need to write K. We need to identify where is A. We want to write K at that position. And then after writing the K, we will move. So similarly, at time 1, we are pointing to the B. We will read B, and after reading B, we write F on that particular box or blank, and then move to right. Now we are pointing to the K. So we are doing three things: reading B, writing F, and moving right. There are three things we have to do when we are moving from Q1 to Q2, Q2 to Q3. We are changing the state. We are doing three things. Number one, we are reading. Number two, we are writing. Or number three, we are moving. Input string. Input string blank symbol. Here you can say there are such symbol. We are representing a special symbol which is called blank symbol. It's a diamond symbol. In some books you will find this type of symbol which is showing which will show you the blank. You can use diamond or this symbol to represent blank. So here you can see input strings A, B, A, C. But what is on the left and right of the A, B, A, C? There are blanks. There are blanks. So all these things are called blank symbols. Head will start at the leftmost position. Normally, when we compute, we normally start from the leftmost position, and then set of transition will do what we are going to compute it. So here a transition, you can see how the state and transition will represent it. You are on the Q1, you are reading A, and then arrow sign separating read and write symbol, and then comma sign separating the reading and writing from the movement. So this symbol is a movement, and this symbol is a read symbol, and this symbol is a write symbol. And there is an arrow which is showing that before arrow is reading and after arrow is writing symbol. So you can read that on from Q1, you read A, write B, and move left, and you are on the state Q2. Or read A, write B, or move right. You can move left, you will write L. For right, you will write R. And you are on state Q. Your output state is Q2. So this is a simple transition representation on the Turing machine. Another thing, you have to represent your current state. When you are on Q1, so the pointer will represent your current state. So we will write Q1 here. Q1, when you are on Q1, your head is on A. It means this transition will take place only when there is reading symbol is A. Otherwise, this transition cannot take place. So if you are Q1, there is a reading symbol A, then you can write B at that place and move to right. Otherwise, not possible. Similarly, on time 1, you will read A, your cursor is on A, and your current state is Q1. After reading A, your transition says when you read A, you need to write B at that place, and after writing, you will move to the right side of the tape. So what will you do? You will read A and you will write B here, and then move to right side of the tape, and the right side of the tape is C. You are pointing to C, and now you are on a state Q2. So your cursor will show your current state Q2. Again, another transition, your pointer is on B, you are on Q2 state. So here you can see from from Q1 to Q2 you move. You read A, write B, and move to left. So if you are on Q1, then you will pointer is on A, and your transition is allowing that you are on A and you can write B, then you can do that transition and your output current state will be Q2, and that will be your time 2. It means it is also showing that time is changing. On time 1 you will be, this is your first action, this is your second action. This will be come first, that will come after the first, and then go on. This is a time series type of execution of program. Lambda transition. How you lambda? Sorry, not lambda. On the input symbol when there is no string, we say lambda. But lambda is not equal to the blank sign. Blank sign is different from the lambda. Lambda means null string, but blank sign means on the tape there is a no input. Both things are different. You are on the Q1, and your cursor is pointing to diamond. It means diamond or blank symbol. So read diamond, write G, move right. So here you can see you have converted the diamond into G, and now you are pointing to another diamond on the right side of the tape, and your state is changed to Q2. Turing machines are by default deterministic. It means you are on the Q1 and your tape having A where you are pointing. Your pointer, your head is on A, then you will go to the Q2. You are on Q1 and your pointer is on B, then it means you are going to the Q3. There is no lambda transition allowed for deterministic Turing machine. You cannot take any lambda transition to move on. By default on the standard Turing machine. Later on, we will move to another Turing machine where we can allow lambda transition. We may allow another type of transition, but the standard Turing machine does not allow lambda transition. We can design such type of later on variants of Turing machines, but standard Turing machine not allow lambda transition, and a standard Turing machine are deterministic by default. Non-determinism is not allowed, means you are on Q1 and input symbol is A and output symbol can be B, you are on Q2, and output symbol can be D, you are on Q3. It is not allowed. It means either it should go to Q2 or it should go to Q3, but not any of one, because determinism is that one transition at a time is allowed. You cannot do, you don't have any choice. Partial transitions. Sometime you can write the partial transition. You hear what type of partial transition is that? You are on Q1 and your cursor is on A. You read A, write B, and move right. It's allowed, but your cursor is on A and you have transition read B, write D. It means currently we cannot move from Q1 to Q3. Okay. If this is the only machine, assume that if it is the only machine and your tape contain symbol C, it means there is no transition for symbol C. This machine shows that if it is your complete machine, then you don't have any transition for C. So how you will stuck up there and this will hang out. And this hanging is called halting. Your machine will halt if there are no possible transition to follow. It means if after reading A, writing B on the place of A, you move to C and your state is Q2. So you cannot move out of Q2 because there is no transition for input C. So that's called halting. No possible transition to follow. Here you can see you are on QC and no possible transition, that it means your machine is halted. Final state. Other interesting thing about the Turing machine is that you can go from non-final to final, but you cannot exit from the final in the Turing machine. In NFA, DFA, we have designed such machine that there are transition, you are moving out of final state. But in the Turing machine, there is no transition allowed to move out of final state. It means if you are going from Q1 to Q2 and Q2 is final, there will be no outgoing transition from final. Here you can see that outgoing transition from final is not allowed. Acceptance criteria for the Turing machine. Accept the input. If machine halt and you machine halt in the final state, it means the input is accepted. A rejection criteria of Turing machine are two. Number one, if machine halt and halt in non-final state, that will be rejected. And if machine halt in by using infinite loop, machine stuck up in an infinite loop, then this is also called rejection. This is not acceptance. This is called rejection. Here you can conclude the point. Another point important. If we insert a loop on the final state, then this point will be invalid. But as we know that we have defined that there is no outgoing transition on the final. So this criteria shows that if you are in final, there is no outgoing transition. You are stuck up in the final and it is accepted. If machine enter the infinite loop and infinite loop, you are not going out of the infinite loop. It means the input Turing machine will not accept that type of machine and that type of transitions. Here is an example of infinite. Read A, write B. You can see that Turing machine A star. Simple machine we are designing Turing machine. A star is accepted by NFA, DFA. A star is accepted by PDA. Then A star is also accepted by Turing machine. Read A, write A, move right. You will read A as many number of A's are there. You will read and move right, move right, move right, move right. Up to there is diamond symbol. It means number of A's are finished. You read diamond, write diamond, and move to the left means last A position, and then you are in final state. It's a simple Turing machine for A star language. But if you change the direction here, if you change the direction in such a way, there you can say there are three A. Read A, write A, move right. Read A, write A, move right. Read A, write A, move right. And at the final state, read diamond, write diamond, move left. Read A, read A, and then final read diamond, write diamond, move left. Halt, but halt in final state, it means machine is okay. Another example, at time 0, you have machine read A, write A, move right. But there is no transition for the input B. You have machine where no transition, it means you are halting, but halting in that state which is not final. It means this will be rejected. This is also a rejection criteria. Another infinite loop language, Turing machine for the loop language. Here you can see if we design a machine in a wrong way, in such a way that read A star, and you design a machine, you have mistake that you write read A, write A, move right, read B, write B, move left. So there is a problem. Read A, write A, move right, move right, move right. When there is a B, you will move left. When there is a you will move right. Let's take some example. Here is ABA. Read A, write A, move right. Read B, write B, move left. Read A, write A, move right. Then read B, write B, move left. This is an infinite input. This this will hang that machine, particular machine, from A to B, then B to A. You design a machine that has incorrect transition and it will stuck up in the infinite loop. And that infinite loop will lead towards rejection because infinite loop is not accepted. It will machine will continue to infinite loop. You normally know that when we forgot the when we insert semicolon on the while loop and on the initial condition, the machine your program will hang. That's due to the infinite loop. Your output will never come, and when the output will never come, it means without wasting time, you just reject that input. The final state cannot be reached. The machine never halt. The input is not accepted. Now come to the A and B N machine. Now, why we are designing A and B N machine? As we know that A and B N is acceptable by the PDA. This is also should be acceptable by the Turing machine because it is more powerful. So first we learn how we can design a Turing machine with the A and B. If one can design the A and B, and then we simply learn that we can design A and B and C and A and B and C and D and A and B and C and D and E, and you can design any type of machine. It will can compute. There is no limitation. So it's a simple machine, just demonstration of machine. I will let you know how it will work. You are starting from Q naught. It's a start state, and this is a cursor that show this is a starting state. You will read a write X, move right. You have transition read Y, write Y, move right. There are two outgoing transition from Q naught. Similarly, if you are on Q1, there are two transition. One is read B, write Y, move left. Another is read A, write A, move right. Another is read Y, write Y, move right. So there are three transitions. This arrow, this loop is showing you can process this type of transition, you can process this type of transition, or any combination of both, permutation of both. If you have B, you will change the state. If you have A, then you will be on the same state. If you have Y, then you will be on the same state. But if you have input B, then you will move to the Y, and then you will write Y, and you will be on the Q2 state. From Q2 state, similarly, there are three transitions. One is going to one Q2 naught, another is on the same Q2 state. If you have Y, then you will be on the Q2. If you have A, then you will be on the Q2. You will write A, read A, write A, and move left, and then we'll stay on the Q2 state. Similarly, if you are on the Q3, there are one outgoing transition which leads to final, another outgoing transition would leads to the same state of Q3. We simulate that machine, and then you will learn how this process. Basic idea should be learned how we have designed that machine. The simple idea that we want to compare as many number of A's are there. We want to compare with that A's with the B's. So keeping in mind the simple idea, there are A, and we want to compute that A's as A should be as number of A's as B's. So number of A's and number of B's will be equal. This is a simple idea. So we will when we have input, we will know that there should be B. If there is no B, then mean symbols are not equal. So we compare first A, then first A will we will search for the first B. When I find first B, then we will come back and search what is another next thing. Next is an A, then there should be second B. If there is a second B, then we'll come back and search for third A. If there is no third A, there are only two A, we will go to the B and check there should not be more than 2B, and machine will stop. This is a simple process through which we execute and machine will run. So this is a simple replacement left to A with X. How we will do? We find first A, we replace that first A with the X. We find first B, leftmost B, and we replace it with the Y. Until there are no more A's or B's, we will continue. When there are A or B are equal and there is a matching, we will stop, and if stopping is in final, then this will accept. So if there is a remaining A or B, let's suppose there are 3A and 2B, then it will reject. If there are 2B's and 1A, then it will also reject. There should be matching. As many number of A, as many number of B, both should be equal. Now, continuing to that, here is input symbol, and we are on the Q1. Q naught, start state pointing to A, read A, Write X, move right. So this transition will take place. Here you can see this transition. First transition is read A, write X, move right. Okay, X, what are X and Y? The students are asking what are X and Y. We are changing the A with X and then we replace again with the A. X will be eliminated from the symbol. Just as we are using intermediate variable. Similarly, similar to the swapping, when you need to swap two variable, you need a temporary variable. Similarly, we are using X and Y as a temporary symbol that are used to compare the number of A or should be equal to number of B. Is a mechanism for comparing. You can use, instead of writing X and Y, you can write L and M, any symbol. There is no problem. I will simulate the machine, then you will learn how it's working, and you will learn very usually. Symbol A, you have input A, you will change input A to the X and move to the right. There is, you will be on a state Q1, and if there is further A, then you will remaining A will be same. You don't change that A because you want to compare first A with the first B, second A with the second B, third A with the third B. Simple strategy is that. So you read first A, you change that first A into X and go to the Q1. Then if there is a B, you change B to the Y and move to the left. And if there is left on the containing the X, you keep that X same and move to the right and check if the remaining Y, there is a Y and nothing to other than Y, you move to the Q3. And after moving the Q3, there is a single A, single B, it means you are at the end and there is a lambda transition, your machine will halt. If there are two A, two B, you will repeat that process two times. So simply, first read A, write B, look at the tape symbol and as well as transitions. You change a first A to X and you are now pointing to second A. You just skipping second A. You don't change the second A. You read A, write A, and then move to the right. Now you are pointing to the B. So transition from Q1 to the read B, write Y, and move to left. Now you are changing first B into Y. You change first A into X and first B into Y. Now you come back and then check, are there remaining A's? Yes, you find A. So you don't change that A. You read A, write A, and move to the left because there is possibility that other A's are on the left side. But when you reach, there is a X instead of A. It means there is no left and there are no A's on the left side. So you are on the again Q1. You have changed first A into X and first B into Y, and you are on again Q1. So from Q1, then you repeat that process. You will repeat that process as many number of A's are there. There should be as many number of B's. You will repeat that process until there will be no A, no B. So again, there is A. You read that A and convert that A to X. You are on Q1 and pointing to the Y symbol. You reach Y, just skip it. Here is a transition. Read Y, write Y, move to right. So it means you are skipping the Y. You are on B. It means the following transition can be moved. Read B, write Y, move left. Now you are changing the second B to the Y. You have to change the second X to the Y and change the second B to Y. Now you come back again by left side in order to check if there is any A remaining. So you skip the Y, read Y, write Y, move left. Then there is X, read X, write X, move left. You are on Q naught, but when you are on Q naught, your pointer is on Y instead of A. because there is no A. So this transition will not take place, which leads to from Q naught to Q1. This transition will take place now, which leads to Q naught to Q3 because you are pointing on to the Y2. So you read Y, write Y, and you are on Q3 state. Now you read Y and write Y and move to right. Why? You want to check, is there any A or B remaining? No. Read Y, write Y, move right. No A, no AB, it means number of A are equal to number of B, and you are on the lambda, you can say diamond symbol has been blank, and this is the last transition which leads to the final. Read diamond, right diamond, move left, and you are in the final state, and you are halting in the final state. It means this string is acceptable. As you know that there are only two and A and two B. A machine is A and B n, which is acceptable by the Turing machine. So this is A and B n machine. If you look and observe, now this is simple strategy. There were A, you converted A to the X. There were B, you converted B to the Y. If you want to design or construct a machine A and B and C, and there is simple strategy. You just add some transition where you have to convert C to Z. So you converted A to B, A to X, B to Y, and C to Z. Then come to check A and convert A to X. Then come to B, convert B to X, Y, and then go to Z. If all these transition, all these symbols are equal, then machine will accept. Otherwise, reject. So we'll pause it to take questions, and you have to design some machines, and there are some basic idea of writing the VV machine, and I have given you basic idea of writing the A and B and C machine. You need to design it. This is your homework. I will check it, and then we'll move forward. I will check your basic idea, how you understand, and then we'll move forward. We'll pause it to take questions.